Welcome everybody, and thank you for joining this webinar on metal replacement in the automotive industry. I'm very excited to have you here. My name is Tim Verage, and for 14-15 years I have experience in the plastics industry. I'm started out in the laboratory introducing new polymer production technologies, having done some scale-ups of new polymers within the industry, and lately I have been working closely with the OEMs and the tier ones in introducing engineering plastic solutions for the automotive industry. And there I also learned that there are some reservations and concerns if it's related to the implementation of engineering plastics. Well, the automotive is a very exciting industry to work in, especially with the new and the latest mobility solutions, new energy vehicles, and a lot of new technologies are being implemented. So let's discuss some of the challenges that we will see. But before we go into those challenges, I will take a few minutes to introduce DSM as a company, and then we will dive a bit further into the trends of the automotive, how you would do lightweighting, and we have some interesting case studies that address all the concerns and reservations that you might have. DSM is a true global company. We have a bit over 20,000 talents working for us around the globe. And as you can see, we are also very concerned about CO2 emissions. Sustainability is a key part that drives DSM and also the solutions that we introduce into the world. So we have a never-ending quest in further reducing CO2 emissions in our plants, but also solutions that we would bring to you. We have a turnover of around 8 billion euro. A large part of our talents are working in Europe, almost 10,000 employees, but we also have a global footprint, and we have a presence of over 5,000 people in North America and Latin America combined, and over 6,000 people in Asia. Our R&D centers are located all over the world. We have a main R&D center in Geleen, Netherlands, but also in Troy, North America, and in Shanghai. Our sales are also covered all over the world. A big part of our sales are actually at the high growth economies where China and Japan take a really important role. We are very proud that we, over the past 10 years, had a top 3 ranking in the Dow Jones Sustainability Index, as that is one of the key drivers at DSM. And we also have been named as the number 2 in the Fortune's list of companies that are changing the world among JP Morgan and Apple. So we are very proud of that. Our involvement in the World Food Programme and also, let's say, all the work that we are doing to leave the world as a better place for the next generations is part of that ranking. So what are we doing in the automotive industry and the electronics industry? As you can see that almost 90% of all the modern cars have materials from DSM in there. And what you can see is that you have typical applications like airbags, chain tensioners, brake boosters, air intake manifolds, engine covers, oil pans, so a lot of different applications where we are able to reduce weight or, for example, wear and friction, and therefore improving the fuel economy. On the right, you see that we are present in every single mobile device around the globe. And we are addressing some key trends like miniaturization, but also the elimination of hazardous substances. And therefore, we have introduced some halogen-free solutions. Of course, also lately, there is a trend that the automotive and the electronics industry are more growing together. And that's also that we see in the solutions that we have in electronics that we are bringing to the automotive industry. If you look at the competences that you would need for lightweighting, there are actually a few. In the R&D center in Geleen in the Netherlands, we combined several of these competences, like, for example, the chemistry. We are able to build different building blocks into our polymers that address the needs of the current automotive industry. We also have the predictive power that we not only produce those polymers, but that we can also calculate how your application is going to work, not only on short term, but also on long term in your vehicle. We have some application experts that can help you in redesigning from metal to plastic to further reduce weight, but also to have an additional performance to that. And last but not least, we are able to do some prototyping with, for example, 3D printing, which can help you to further reduce your design cycles. What is one of the key challenges in the automotive industry? And that is that over the past 50 years, the average weight of the passenger vehicles has been growing with 10 kilograms every year. And you can imagine that it adds up to a few hundred kg. And that's also for a good reason. Over the past decades, more safety systems have been introduced, like ESP, ABS, and even lighting now can be added to that category. We have been increasing the customer experience with air conditioning, infotainment systems, a further increase in connectivity, and lately also looking into autonomous driving. So more sensors are, for example, being built in. And all of these systems, they also require technologies that have a certain weight to it. So lightweighting is very important to accommodate these type of new technologies. Furthermore, new energy vehicles are being introduced, alternative powertrains, for example, electric driving, where you have to deal with relatively heavyweight batteries. You still want to keep a certain driving range. So lightweighting is important. And last but not least, the reduction of CO2 is of course very important. Legislation is further tightening. Towards 2025, we have to reduce around 44% of CO2 emission, and lightweighting is one of the key solutions that can be used. So the reduction of CO2 of almost 44% by 2025, that means that in the end, a car has to lose weight, a significant amount of weight of almost 200 kilograms. And the question is how to do that. There are a few alternatives out in the market. You can go from steel, you can go to aluminum, which only 1/3 of the relative weight. And that helps already a lot to further reduce the weight. A second option is to increase the amount of plastics that you are using in your car, and then specifically for structural parts in body and bite structures. But how to do that? Of course, introducing engineering plastics to the automotive industry is not new. From around 30,000 parts in a modern car, 10,000 parts are already from plastics, ranging from bumper exterior parts to interior parts, but also more and more structural parts are being included. From chain tensioners, brake boosters, oil pans, engine covers, and many more of those. So if you look at this, you see that the first step in weight reduction is going from steel to aluminum, and the second step is going to engineering plastics, which can further reduce the weight with 50%. And that's of course a significant contribution. So what kind of applications could you actually target? What we see is that some of the relative easy parts have already been converted to metal. But there are some challenges also in other parts, like for example, engine mount, engine brackets, lighting brackets, a lot of housings and covers for sensors, electronic power steering systems, ECUs, etc. Many of those are still in aluminum die cast, and they could be replaced with engineering plastics. These type of structural parts, they have of course a lot of specifications, and they often have to operate in a broad temperature range from -35 degrees C up to 150 degrees C, and still keep their strength and their stiffness at these high temperatures. Sometimes these high temperatures are not required, but you only go up to 50 or 80 degrees C, but then with a very high relative humidity. Also, if your car is parked in Singapore and you start driving with it, you do not want to have any influence of, for example, moisture on the stiffness of your part. So dimensional stability and accuracy are also very important. The mechanical performance of any structural part, of course, has to fulfill the static and also the fatigue specifications to ensure that over the entire duration, the entire lifetime of your car, you still have an accurate performance. A fourth one is NVH, so noise, vibration, and harshness. Sometimes plastics can help you with a structural part to increase the damping performance. And there you need a combination of high stiffness and damping. For example, an engine mount would benefit from that. At last but not least, chemical resistance is important. Most of these parts come in contact with road salt, engine oil, transmission oil, grease. You can have a battery acid spill, meaning that the engineering plastics has to keep their integrity if they come in contact with these kind of chemicals. As said, most of these parts are still in aluminum. So how to choose between an aluminum or an engineering plastic? If you take aluminum, for example, an alloy A380, which is commonly used in the automotive industry, you see quite some advantages of using these type of materials. One of the key advantages is actually the linear part performance up to 200 degrees C. Of course, also after 200 degrees C, the strength and the stiffness of aluminum starts to drop. But up to 200 degrees C, you have a very good predictability on how your part would behave. That's often more difficult with engineering plastics. But also lately there are some new developments that would allow you to go to high temperatures and still are able to calculate with a linear part performance. If we compare it, for example, to PPAs, PA4T, that can be used for injection molding, you also see some advantages of using engineering plastics. So besides the 50% of weight reduction that could be achieved, you also can achieve some cost reductions. We mostly see around 10 to 30%. And that mostly has to deal with smart design, less weight, less material, thinner ribs. So also there the injection molding cycles can be, cycle time can be reduced. And you gain some high production efficiencies. So often if you want to go to high series, a few 100,000 of parts, then injection molding with engineering plastics can be a real benefit. But what about the part performance? What about the temperatures to be achieved? With PPAs, you can push the boundaries, and we see that PPAs could be really the next best alternative to aluminum. With glass transition temperatures up to 150, 160 degrees C, we see that these materials can be used and are as strong as aluminum up to around 120 degrees C. But of course, there are also some reservations. There are some concerns when going from metal to engineering plastics. A lot of these you probably will recognize, and if you are a designer or an engineer and you have to go from metal to plastics and you do not have too much experience with that, you see a lot of difficulties. It's difficult to predict the part performance. What if something unexpected happens, as a battery spill, a battery acid spill, or the peak temperatures goes higher than what you expected? There are a lot of situations in where you can feel insecure about what is going to happen to the plastic. So that also means if you take a step and go from metal to an engineering plastic, you also need to make sure that you choose the right engineering plastic. Here at DSM, we also know that it's not about the data sheet. So we do extensive testing of our materials and parts that are relevant to you and to take away a few of those concerns. So let's dive a little bit deeper in three topics that are very relevant if you engage in a journey from metal replacement to an engineering plastic. So first of all, which plastic to choose? which polymer to choose. How do you do that? Let's first address that topic. After that, we go into testing and predictability. So the predictive power of the material that you're going to choose is absolutely important to make an assessment of which material to select, how the material will perform over the lifetime in your application. And last but not least, processing is also very important. Let's start with choosing an engineering plastic. Here you see a triangle that addresses quite a few of engineering plastics that are out there in the market. There are actually two categories. One of them is the amorphous part, and the second one is the semi-crystalline materials. For example, polypropylene, so the polyolefins, the polyesters, the polyamides. And we will focus on these semi-crystalline materials because they are often used in the automotive industry to replace metal parts. So if you look in engineering plastics, you see a few buckets, a few mainstream materials that are often being used. So the first one is PP, so part of the polyolefin cluster. Then you have the polyesters with PBT and PET. You have the PPS materials, often used in combination, for example, with thermal management. They are excellent for the chemical resistance, very low moisture absorption. And as a fourth bucket, you have the polyamides. Polyamides like polyamide 6 and 6,6 are very often used for metal replacement in the automotive industry. Actually, in the polyamide family, you have two different subsegments. The first one is the aliphatic polyamides, polyamide 6 and polyamide 6,6. Especially polyamide 6,6 is one of the key materials being used, and we also will use that as a benchmark during the comparisons with aluminum, but also with the PPAs that we are going to introduce. The second part are the semi-aromatic polyamides, and with the semi-aromatic polyamides, the so-called PPAs, polyphthalamides, you see that there is a ring structure introduced in the chemical, in the polymer. And with that ring structure, you gain a few features that are very relevant if you want to replace metal into an engineering plastics. And we will dive a little bit deeper into that field. So let's start with the polyamide 6,6. If you look here, you see on the left side, you see the stiffness of this material. And on the horizontal axis, you see the temperature. And what you typically see is that it's not a linear performance. There are a few points very important on this curve. The first one is, of course, the melt temperature. The melt temperature for a polyamide 6,6 is somewhere around 255 degrees C. So that means if you reach peak temperatures above that, you will end up with a very fluid polymer, and this material cannot be used. You have the crystallization temperature, also very important, because below that your material gets its structural integrity. And the third point is also very important, that is called the glass transition temperature. And this glass transition temperature actually represents a large step in the performance of your material. Below the glass transition temperature, you have a very rigid, very glassy state, and below that you have a more rubbery state. The glass transition temperature of a polyamide 6,6 is around 70 degrees C. And on the top right, you see the chemical structure of such a polyamide 6,6. In the middle in blue, you see the amide group that is bonding two different monomers, two different building blocks. On the left, you see a diamine, and on the right, you see a diacid. So as said, these materials have a glass transition temperature of 70 degrees. So that means the stiffness and the strength drops significantly around 70 degrees C. But what if you would introduce a ring structure in this polymer? If you introduce a ring structure in this polymer, a lot is happening. You can actually increase the glass transition temperature from 70 degrees up to 150 or 160 degrees C. So these type of polymers, they are called PPA, and DSM has a PPA that is based on the PA4T technology, and the T is representing that ring structure. So you increase the operating temperature already. Furthermore, you increase the melt temperature. It goes up to around 230, 240 degrees C, meaning that you also can accommodate for much higher peak temperatures. So if you make a summary of the advantages of a PPA above a polyamide 6,6, you would summarize it as increasing the broader temperature range due to the higher glass transition temperature. And you can accommodate for higher peak temperatures due to the higher melt temperature of these materials. NVH could be improved because that is a combination of stiffness and damping. So all that stiffness, as you can see, is increased to a higher temperature range. PPAs also show a much lower and slower moisture absorption. So that means that the strength and stiffness are not that much influenced by moisture as it is with a polyamide 6,6. A polyamide 6,6 can already absorb the maximum amount of moisture in around 1 to 2 weeks, and a PPA that takes over half a year to absorb that amount of moisture. That also means that the dimensional stability of a PPA in general is higher than for a polyamide 6,6. At last but not least, the chemical resistance of PPAs is much higher than with a polyamide 6,6. So that does mean that you do not have to worry about road salt, engine oil, transmission oil, all kind of acidic environments that you could have in a car. That also makes PPAs very suitable for thermal management parts, because it can deal with water glycol resistance. So if we go make a short recap with aluminum die-cast, polyamide 6,6, and the PPAs like polyamide 4T, you see that with choosing the right polymer is very important for your part. We already addressed the temperature range, which is a very important one. With aluminum, you can make a design up to 200 degrees C, where you still keep stiffness and strength. With polyamide 6,6, you see already a significant drop in strength and stiffness at 70 degrees. And with PPA, you can make a design up to around 150 degrees C, meaning that with a PPA, a PA4T, that it is really the next best alternative to aluminum die casting. You have further advantages in, for example, dealing with harsh environments, because the chemical resistance of these PPAs is much higher than a 6,6 or actually the aluminum. And of course, obviously, you have a weight reduction potential of up to 50% and a further cost reduction potential of 10 to 30%. So what can you actually do with PPAs? What we see here is on the horizontal axis the strength and the stiffness of a part. And of course, you can work with a very low temperature up to around 70 degrees C with a polyamide 6,6. After that, you can expand the temperature range with a standard PPA. But typically, those standard PPAs, they tend to be a bit more brittle at lower temperatures and room temperature. So standard PPAs are normally used in thermal management modules, coolant applications like valves, water baffles, water pumps, and fuel components. At DSM, we designed a PPA called PA4T with 50% of glass that pushes the temperature up to around 160 degrees C, which is unique in the world. That means that you can do metal replacement in, for example, transmission components, where you have to deal with transmission oil at 100, which is relatively aggressive at 150 degrees C, fuel components, but also you can actually eliminate metal inserts because of the low creep of these type of materials. But is this also enough for structural parts? If you look, for example, at an engine mount or a housing, they also have to work from minus 35 or minus 40 degrees C up to around 150 degrees C. It has to work over the entire temperature range. And with this latest innovation, with this latest material, 40ACE MX53T, we are able to expand the scope of PPAs really into load-bearing structural parts for the automotive industry. And that's unique in its kind, and that's something that we will dive a little bit deeper in. So as a short recap, PA4T outperforms polyamide 6,6. But what about aluminum? Is it really as good as aluminum? What you see here is the performance of an aluminum alloy at room temperature in blue and 120 degrees C in gray. And what we did is we divided the specific material, the tensile strength of this material over the density. And then you get the specific material strength. But what about PA4T? If you look at the specific material strength of polyamide 4T with 50% of glass, you see that at room temperature it actually outperforms aluminum. And at 120 degrees C, it is on par with aluminum, meaning that these type of materials can be used to replace aluminum. So the 4T materials are PPA and they are based on the strong PA4T technology of DSM. ACE MX53T contains around 50% glass and is very suitable for aluminum die-cast replacement. So you can actually achieve the 50% of weight reduction and the cost reduction. Due to its low and slow moisture absorption and chemical resistance, it's also a very robust design. It enables designers and engineers to realize a real robust design. Question, of course, this is all nice, but is it also tested in real parts? And there we want to show you a bit on how we design at DSM. So some testing and some predictability. We know it's not about the datasheet, it's all about the part performance. And that's also why we do not design our materials based on a standard tensile bar or a notch tensile bar. But we make parts like bending beams, load brackets, EPS housings, and we test them extensively to see how the materials behave under static load conditions, but also under fatigue conditions during the lifetime of your part. What we see is that with ACE MX53T, that we have a consistently higher performance of up to 40% compared to other PPAs from minus 35 degrees up to 150 degrees C. So let's take one of the case studies. If you have an electronic power steering system in your car, you actually have two different types, but they all contain a housing, and that housing is mostly in aluminum die cast. They weigh around 1.1 kilogram. Mostly multiple machining actions are required to meet the full dimensions. We are able to replace that with a polyamide 4T with 50% of glass, reducing 50% of the weight and around 10% of the costs. Typically, these parts have to perform from minus 35 degrees C up to 120 degrees C, need a very high dimensional accuracy and stability, good surface quality, and of course they have to be able to deal with the road salt. So how would a design like that look like? At DSM we have the capability to design our own tools. So here you see how we designed the tool for the EPS housing demonstrator, and we also actually designed the cooling channels in that mold to make sure that we have a good controlled production tool that we can use for making these type of demonstrators. Then the whole work starts. What kind of predictive power do we have? Well, if you have an EPS housing, there are two load cases that we normally use. We put a certain static load on these parts, and we're going to check when these parts are going to break. First of all, of course, we're going to predict that. We're going to simulate at which kind of maximum loads these fractures occur. And then we're going to see in practice how that matches up. At this moment, we are able to simulate where and when a part breaks within 10% of accuracy, which is an enormous high value. Of course, before reaching that stage, you have to do a flowability analysis, look where the weld lines are of your part to see that they are not in critical areas where you have high stress concentrations, so we are able to optimize the design. And then, of course, we go into the failure prediction and then compare it to testing. So at this moment, we are able to do that with a 90% accuracy. And this is about the static loads that we see on a part. But what about testing it for long life? There we have used, for example, a demonstration part that is called a load bracket, which resembles an engine mount. There we are able to test the longevity. And what you see here is one of the test setups that we have available at DSM in our Geleen research facility in the Netherlands, where we typically test those parts. And because the predictability is that high, we also know that we can help you to design safe and robust parts. So having covered the choice of the engineering plastic, the testing and the predictability, but what about the processing? In the end, we also have to realize those parts. How difficult is it to injection mold a PPA in comparison to a polyamide 6X? Well, we know that the processing is very important because in the end you have to realize mass production. And therefore, during the design of our materials, we take processing into account. A few things are very important. First, we want you to be able to work with standard hardware that you can get from different injection molding suppliers. And that's also the case with the 40 and the 40 ACE materials. You can use standard polyamide hardware for high glass-filled polyamides. We also see that there is no corrosion or melt deposit for the 40 portfolio that is being used for metal replacement. Furthermore, residence time is very important. Which kind of machines can you use, which kind of tools, how big are the applications that you can actually make. So therefore residence time is very important. Our unique production process of our 40 portfolio also allows for a high residence time. But of course, I can imagine that you also would like to see some proof. What we typically do is we do a lot of design of experiments. We do extensive testing of the materials on different machines under different settings to ensure that you can have an easy and robust processing. This is a typical example, a part of that of the DOE that we have been doing for 40 ACE MX53, so the PA40 with 50% of glass. We made a variation, for example, in the melt temperature, in the residence time, and also in the mold temperature. And then we're going to assess the modulus, stress at break, and for example, the elongation at break. And what you typically see is that within the operating window, with the melt temperature, the residence time up to the melt residence time up to 4 minutes, a mold temperature from 80 degrees up to 200 degrees C, that there is very limited variation in the stiffness of the material, the strength, and also the elongation at break. So the materials in our portfolio for metal replacement are very stable in processing, and that's also the feedback that we get from our customers, like for example VDL. So we have covered now a few very important topics in the field of going from a metal to an engineering plastic, how to deal with the prediction during lifetime and also with processing. So what are the takeaways of this webinar? What are the takeaways of this? The automotive trends, again, they have to lose around 200 kilograms of weight for various reasons to improve the fuel economy and also open up the opportunity to go to new energy vehicles. In total, we have to reduce the CO2 emission by around 44%. And that's a very challenging task. Going from metal to aluminum already helps with reducing that weight significantly. But also a next step can be taken from going from aluminum to an engineering plastic. Around 50% of weight reduction can be achieved. And there is also the potential to reduce the cost with around 10 to 30%, depending on the secondary operations that are normally needed for the aluminum die-cast operation. We see that polyamide 4T with 50% of glass is one of the key materials that can be used to replace aluminum. Due to the fact that it has the high chemical resistance, low and slow moisture absorption, and it's almost on par with the strength and the stiffness of aluminum, that you can have a very robust solution. We are able to predict with around 90% accuracy, and we have tested the material extensively in real parts. So if you are looking forward to taking up that challenge, we have the right materials and also the right competences to help you with that.
And this concludes today's webinar. Many thanks for your attention, and for more information you can visit any of the shown websites.